Yesterday we defined Cauchy sequences, and I'm going to use this to define real numbers. So any Cauchy sequence, by its definition, in the limit, okay, so let change this. Take the limit n tends to infinity of the numbers which are rational numbers, an in the sequence. This limit exists by virtue of the fact that successive numbers in the sequence are closer and closer to each other. So it is going to converge to a number, and that number is I'm defining to be a. And one can show again by using the property that its successive numbers are closer and closer to each other, that this limit is unique. That is, if there are two numbers with the same limit, then the difference will go to 0. Okay. And this number a is, we call a real number.
Like in harmonics, terms are closer, but it does not converge.
Some of it doesn't converge. But if you just look at the harmonic an is 1 by n, that take the limit, it goes to 0. Terms goes to 0. So that limit of harmonic series kind of Cauchy sequence is 0. So what's the advantage of defining a real number in this way? One thing we can say is that all real numbers can be expressed in this fashion, and everything that is expressed in this fashion is a real number. That's the intuitive notion of real number, does match with this definition. But what is clear is that there are multiple Cauchy sequences converging to the same real number. Like 1 by n, that limit converges to 0, 1 by n square limit converges to 0, 1 by n cube converges to 0. So that's not really solving the problem that I stated earlier. But it solves one or two other problems about real numbers, which I am fairly sure you did not pay a lot of attention to whenever you came across real numbers. So let me ask you, if I give you two real numbers, can you add them? If yes, then how? Can you add two real numbers? How? You know how to start with? Where is the rightmost? There is no rightmost. It's forever, for infinitely long sequence. It's not computationally. I'm not asking the design an algorithm. Of course, you cannot design an algorithm, but at least conceptually, can you figure out a way of adding that?
Series of rational numbers.
That we can write, sure. Given real number, let's say this kind of infinite size inputs can be viewed as the following, that you are given access to a black box where if you put a number m, you get the mth digit of that real number, mth digit after the decimal point, let's say. So if you are given such an access to two real numbers, and you want to, now you can actually talk about an algorithm to add these two. And this algorithm takes as input, of course, these two black boxes, and also a digit number k and produces the kth digit of the sum after the decimal point. How do you do that? That's how the representation of the decimal representation of real number. That's what it means, that you should be able to produce, given a k, you should be able to produce the kth digit of the number after the decimal point. Any number, whatever, not just kth digit, but we can say, okay, give me k plus first digit, k plus second digit, 2 kth digit, all the digits we can access them. But the question is, what are the carries? How do you know the carries? You won't, because it goes on forever, and there is no pattern in that in general. So you can't really, with this the understanding of the representation we have of real numbers, we can't even add them. Of course, we can't multiply them either. You can give an error bound, yes, but nothing beyond that. So even addition or multiplication on real numbers in that representation is not well defined. And that's a bigger problem with that representation. It does correspond. Somehow it's intuitive to an extent, but it doesn't quite work for real numbers. It only works for rational numbers. So that's why you need an alternative representation to define such operations. And Cauchy sequence is perhaps the best such representation, the simplest such. Because now we can define, now that a Cauchy sequence represents a real number. So now addition of two real numbers so we are given Cauchy sequence, so let's say an and bn plus bn. I can define it as simply as this sequence. Just component-wise addition. This is a Cauchy sequence, an plus bn. Why? You just need to verify that property that given an epsilon, there should be a large enough n such that an plus bn, the difference of this with a n plus m plus b n plus m is smaller than epsilon. And that's done simply for, let me just show it for this, and then I'll not do for multiplication, you can do it yourself. Consider that n So pick that NA for the AN sequence such that the difference is at most epsilon by 2 after NA, and similarly NB for BN such that the difference is also less than epsilon by 2. And let N be the max of NA and B. Then A n plus m plus b n plus m minus a n minus b n. This less than equal to if you look at this difference, that's bounded by epsilon. So we have shown that same property for this sum sequence, right? And similarly, we define multiplication. Just the component-wise product. And the same property can be shown that this is also a Cauchy sequence. And it converges to the product numbers, and that's easy to see. Okay. So now it's very easily defined, and that's one great advantage of now at least we know what addition and multiplication means over the Cauchy sequences. Now that we have it, so we therefore get, if we define, let's say, R script to be set of all Cauchy sequences. We have this lemma that script R is a ring under addition and multiplication. Because there is one sequence that is, say if you look at the addition, all zero sequence is the identity of addition. The negative ANs is a inverse of AN, and for multiplication, all one sequence is the identity of multiplication, and the multiplication distributes over addition because component wise is just a multiplication and addition of rational numbers. So all those properties are satisfied, and therefore we get a commutative ring. It's an infinite sequence.
That is also formal power series.
Formal power series is an infinite sequence, yes, but there the coefficients need not have a particular pattern of the kind we want. So here we want very strong pattern, that is successive numbers must get closer and closer to each other. Okay? So we have a ring, but we still haven't resolved the problem of multiple representations. In fact, let's look at all representations, all Cauchy sequences that represent the number 0. So let I be the set of all Cauchy sequences which converge to 0. Because the name gives it away, this is going to be an ideal. In fact, not only any ideal, it's a maximal ideal. Firstly, why is it an ideal? It's a commutative group under addition. That is closure under addition. If you have two Cauchy sequences, both converging to 0, then their sum also converges to 0. Clear? If you have a Cauchy sequence in I and multiply any other sequence to this, that would also converge to 0. Because if an converges to 0, then an times bn, as long as bn's are bounded above by some number, it also converges to 0. So it's clearly I is an ideal. Why is a maximal ideal? That's a question. Well, okay, let's pick up any Cauchy sequence that's not in I. What does this mean that Bn is not in I? It means that Bn converges to this converges to, let's say, B, and B is not equal to 0. Now let's define the following Cauchy sequence, which is let's define another sequence or numbers. These are rational numbers b hat n, which take the value bn whenever n is less than or equal to capital N, and 1 over bn whenever n is greater than n. And capital N is number chosen so that after capital N, bn is not 0. That such a capital N exists follows from the fact that the bn sequence converges to a non-zero number. So there will always be a large enough capital N beyond which bn is never going to be 0. Because it has come so close to b that it can never become 0. Now, so here let me give you as an exercise. That b hat n is also a Cauchy sequence. Converging to 1 by b. Once we have shown this, then the rest is straightforward. Even this exercise is not difficult at all. But once we have this, then just consider the Cauchy sequence which is obtained by multiplying b hat n with bn. This is a Cauchy sequence. How does this look like? Equals some numbers up to first capital N numbers. After that, it's all ones. Directly by definition. Multiplication of b hat n with bn.
Multiplication b hat
Yes. See, if you look at the definition of b hat n, above capital N, it is 1 over bn. So 1 over bn times bn is just 1. So all the numbers beyond capital N will be 1. The numbers below that may or may not be 1. In fact, let me write this, give a name to these. Let's call them C1, C2 to Cn. These are some rational numbers. Also now note that this number or this sequence, which is first n numbers are C1 to Cn and all the subsequent numbers are zeros. This is the Cauchy sequence, clearly, because it's converging to 0 and beyond a point everything is 0, all the differences are 0, and this belongs to the ideal I. Now what is the difference between these two? So let's call this sequence C. Then B hat n times Bn minus C1 to Cn this is the first n numbers are C1 minus 1, C2 minus 1 up to Cn minus 1. All other numbers are 0. It is still a Cauchy sequence. Actually, Cauchy sequences have this property that first few numbers can be arbitrary, doesn't matter. As long as after a certain point everything starts converging. So this is the Cauchy sequence, it converges to 0, so it's in the ideal I, and the difference between this is all ones. This is the one. So now we have the Bn was a Cauchy sequence which is outside the ideal. This is in the ideal. So in the ideal generated by Bn and I, we get the 1, which is therefore it's an entire ring, and therefore this shows that I is a maximal ideal. Add any other any new element to I, you get the whole ring. Now we can define our class of real numbers. R to be script R quotiented with I. This will have a unique number or unique element corresponding to every real number. And since I is a maximal ideal, it's a field. So this is the formal definition of real numbers. Somewhat non-intuitive, a little more complicated, but this is the way you can properly define real numbers. Not in earlier, the school definition is very informal. Sorry? That's always with, see, when you actually are working with numbers, they are always rational numbers. So that's why that is fine.
Now addition and multiplication will be in this quotient ring.
In the quotient ring, yes. And now multiplicative inverses also exist by virtue of this being a field. So this process, the whole thing that I went through, starting with rationale, defining the Cauchy sequences, then quotienting the ring of Cauchy sequences with a maximal ideal to get another field. So of course this also involves that quotienting an ideal with a maximal field to get a maximal ideal to get a ring, to get a field. But there is something else done, which is you start with a field, you introduce Cauchy sequences of that field, and then do it this way. This process is called the completion of a field. And this we can define for many other fields, not just with rationals. As long as we have a notion defined of nearness, right? Two numbers are close to each other and they can get closer and closer to each other. So that notion must be available on that field. and we can define completion. So in particular, for example, we can ask what is the completion of R itself. That is, you start with R, define Cauchy sequences with elements of R, get that ring, quotient, maximal ideal, quotiented, get a field. What do you get? And it turns out that that's a theorem. Get nothing new. You get back R. So we are not. R is therefore, in a sense, the ultimate or the final point where we can extend this completion, starting from rationals, of course.
Something like one gap between rational numbers.
Mm-hmm. That's right. That's what the completion is. That's how the name derives. That you complete this gap between rationals. That's right. And this whole process, if you see Cauchy sequences, etc., that is trying to fill that gap. Okay, so that's all I will talk about this completion. Let me get back to the fields, and we were discussing ways of getting fields from rings. One way was quotienting with maximal ideal, another way was starting with the integral domain and taking the fractions. That's also a field. Now, in order to do that, we have to start with integral domains, which not all rings are. But starting with a general ring, we can actually get very nicely integral domains. That's the next theorem. Take a ring R, take its ideal I and quotient R with I. The ring you get is an integral domain if and only if I is a prime ideal. Proof is straightforward. Let's say A, B be elements of the ring not in I. Now consider the quotient ring. The quotient ring will have elements of this form. This is equal to AB plus I. Now if, in fact, why started? Let's start with general two ring elements. And in general this is true. Now if AB plus I is in I, this implies that AB is in I. In fact, this is if and only if. Why? Goes both ways. And now let's say, suppose R by I is not an integral domain. What does that mean? That means that there exists A and B such that A plus I and B plus I are non-zero elements of this quotient ring whose product is 0. So that means A plus I times B plus I, which is AB plus I, is 0, which means this is 0 meaning that AB is in I, right? And A plus I and B plus I are non-zero, which is equivalent to saying that A is not in I and B is not in I. Such that AB is in I. And this implies that I is not prime. That's by definition. Conversely, if I is not a prime ideal, that means there exists such that AB is in I. And this implies if AB is in I, then AB plus I is equal to I. And this implies it's not an integral domain. It's pretty straightforward. So now we have this way of creating fields as well. Start with any arbitrary ring, take any prime ideal, quotient with the prime ideal, you get an integral domain, and then take the field of fractions. Now the fields are a special kind of rings, of course. They are very interesting because the full arithmetic can be done here. These are the only structures where the complete arithmetic is possible. All four operations, addition, division, multiplication, subtraction, can be carried out completely. And therefore they are extremely useful. So we would like to understand their structure as well, just like we try to understand the structure of groups and rings. So let's try to understand structure of fields. And one of the key parameters associated with a field, because firstly we must realize that fields have more structure than rings, because division is also available. They have to satisfy, everything is a unit, so those strange elements which are non-units don't exist in a field. So it's expected that it should have more structure, and it is indeed true that fields have more structure, more things can be proven about fields than for rings. And one of the key things or key parameters associated with the field is its characteristic. The characteristic of a field is the smallest number n, such that when you add 1 to itself n times, you get 0. Now these 1 and 0 are the identities of the field. There would be fields where no such sum would ever be 0. For example, for rational numbers, you keep adding 1, the number keeps growing up, it will never become 0. Okay? So let me add that if no such n exists, then If no such an exists, then f is said to be of zero characteristic. Otherwise of characteristic n. Okay, because zero characteristic, because it's doesn't quite fit into that, but really if you add 1 to itself 0 times, of course you get 0. That is true with everything, but that's the only way possible in some fields. So that's why you call zero characteristic. So examples. Characteristic 0. These are rationals, reals, complex numbers. Field of rational functions over f. These are all characteristic 0 fields. Oh, wait a minute. F where this field where f is of 0 characteristic. Otherwise, finite characteristic. ZP. This is a field, right, which is obtained by Z quotienting with prime or maximal ideal P. And this is of finite characteristic, because in this field, if you add 1 to itself, P times, that's 0.
Polynomial ring over this.
Or yes, then more often written as FP, to highlight the fact that they are fields of characteristic P. FP. This also has characteristic. In fact, there is another simple to prove theorem, but important one. That characteristic of a field can be either 0 or a prime number. I leave the proof to you. It's very easy to show. So what is the structure of fields in general? The answer is not straightforward at all. Even though fields have more structure, there are all kinds of fields. Particularly when we talk about infinite fields. There are of various kinds. I'll want to highlight one special kind, which is algebraically closed. But before that, let's me highlight one very important property of fields, which is the also called the fundamental theorem of algebra. Have you come across this? The fundamental theorem of algebra? No? I'm sure you have come across it. When I state it, you will realize. So take a field f and take a polynomial p in one variable x with coefficients coming from the field f. Such a polynomial is called a polynomial over the field f, okay, because its coefficients are from the field f. Let degree of p be d. You seen this? That's a fundamental theorem of algebra. You must have seen this for specialized to specific fields, reals or complex numbers. But this holds in general over all fields. And the proof is same as the proof for the special case, in case you recall it. So we can prove this by induction. So for d equals 1, p is cx plus c prime. This implies that there is exactly one root correct. Notice that c is not 0 because of degree 1. So x is 0 is the only root. Okay. Now induction step. Assume for d minus 1, now we want to prove for d. Let alpha in f be a root. Okay. Then px is same as px minus p alpha. Okay, which is same as summation I going from 0 to d, let's say ci x to the I alpha to the I. Since p of alpha is 0 by assumption, so I can just write it this way. Now, if you look at this two difference, you can take term by term a common factor of x minus alpha. Ci x to the I minus ci x alpha to the I. Take a factor of x minus alpha out and collect the rest in this p hat x. Now, p hat x is a polynomial of degree d minus 1. Now the rest is straightforward. Now you just invoke the induction. This will have at most d minus 1 roots, p hat x by induction. And what are the roots of p? Any root of p hat x plus alpha, that's possibly the dth root, the one more, and no other. Any other value of x where x minus alpha is non-zero and p hat of x is non-zero will result in non-zero value because it's an integral domain. So product of two non-zero values will remain non-zero. In fact, this property holds not only for fields but for any integral domain. So that's all for today. We will continue tomorrow.